Hey, how are you doing? So we're going to try to do some sensitivity analysis today. And so if you look, I've got us an LP written up, and I've already converted it to standard form and put it in a simplex table. And I know that after a few pivots, the optimal basis has x2 and slack2 as the variables taking value. Those are the basic variables. Okay, so we're going to use this fact that these are the basic variables to perform sensitivity analysis. And so let's start by performing sensitivity analysis on, let's do cost 2. Okay, that just means the second cost, 2, 3, so there's our second cost. So we know that C2 is equal to 3. We would like to consider if we can change it, how much we can change it and stay with this basic variable group as our optimal and as it being for it to stay feasible. Okay, now we technically don't have to worry about feasibility changing a cost because it's not going to have any effect on the right hand sides going negative or not. But we do need to make sure that if we change one of these costs, that x2 and s2 are still the only two that are in the basis, and that x1 and slack1 do not become attractive to enter the basis. So the way we're going to do this is we're going to check that all these variables stay greater than or equal to 0 at this final simplex table. And the way we're going to do that is we're going to use matrix multiplication to generate what these numbers will be there. And now that formula is CB times capital B inverse times A minus C. And so we need these vectors and matrices to be able to do this arithmetic. All of these are going to come from the original simplex table. They're all right there for us. The easiest to come up with is capital A because that is just this body right here. So I know capital A is 1, 1, 1, 0, 2, 1, 0, 1. So there's capital A. Minus off the cost. And the cost is actually really easy, an easy vector to have too, because the cost is technically the opposite sign of what's sitting here, 2, 3, 0, 0. So we need to come up with CB and B inverse. How do we find those? That's actually pretty easy. What we do is we notice that the basic variables are x2 and slack2. And so if we go to x2 and slack2 and look at their cost, remember these are their opposite signed, 3 and 0, that makes our CB. CB is 3 and 0. Okay? Now, we need B inverse. Well, where does B come from? Well, that's actually the pieces of A that come from these basic variables. So x2 and slack2 are basic, so just grab their columns out of the A matrix, 1, 1, and 0, 1. Then you can use a calculator or a program, or you can do it by hand, and we try to get the inverse of that. So let me not say equal. Let me draw a little arrow and say, okay, well, let's find B inverse. And B inverse is 1, 0, negative 1, 1. Okay? And so let's plot that over here. Now, this would tell us what these reduced costs across the top will be when we're at optimal. That would be for C equal 3. But what am I wanting to consider for my new C2 value? Instead of 3, which appears here and here, I want to consider 3 plus delta. So let me add in, I might need to erase a little bit to fit it. Let me add in this plus delta. And I think oops. Let me stop. So let me try to fit in this 3 plus delta. Alright, let me grab glue and put back in these other pieces. Alright, so I just need to be able to perform matrix multiplication here. Now it's going to be annoying because there's a delta in there. But if I can perform this matrix multiplication and matrix subtraction, I will have all the reduced cost in terms of delta. And then I can figure out where we stay optimal. Now, because matrix multiplication is associative, I can go ahead and do B inverse times A, and that'll make life a little bit easier. So let's see here. So the way you multiply a matrix is you go row by column. So if I go row by column, I'm going to get 1 times 1 and 0 times 2. Add those together, that's just 1. Right? And we're going to do this first row times each column to get this first group of things right here. Okay? So that'll just easily be 1, 1, 1, 0. You can check me on that. And then this bottom row is going to be row by column. So negative 1 times 1 and 2 times 1. So that's negative 1 plus 2 is 1. Negative 1, so this entry is going to be 0. This entry is going to be negative 1. And this last entry is going to be positive 1. Okay. Alright. So now I need to perform this matrix multiplication, which is going to be a little bit annoying since it has a delta in there, but that's not too hard. We can do this row by column, row by column, row by column, and so on. So let's see what we get. So that will be 3 plus delta in the first spot, 3 plus delta in the second spot, 3 plus delta in the third spot. I made this too easy, huh? And 0 in the fourth spot. And you can slowly double check my matrix multiplication here. It's 3 plus delta times 1 plus 0, 3 plus delta times 1 plus 0, 3 plus delta times 1 plus 0, and 3 plus delta times 0, 0 plus 0. And now I just need to do this subtraction. And so if I do 3 plus delta, when I minus vectors like this, subtract vectors, I just do each piece one at a time, each entry. So the first entry minus the first entry, 3 plus delta minus 2 is 1 plus delta. And then look at the second entry, 3 plus delta minus 3 plus delta, that's just 0. 3 plus delta minus 0 is 3 plus delta, and 0 minus 0 is 0. And so here we are looking at the reduced cost if I were to have a delta in at the last table. Now to stay optimal, we want all of these values, each value to be greater than or equal to 0 so that there's no attractive values to enter the basis. Well, these are already in the basis, so notice they are still 0 like they should be at the optimal. So we're just going to check these two to make sure to see where we need to stay greater than or equal to 0. So I'm going to take these pieces, set them greater than or equal to 0, and I will solve for delta to see how much change I can have. So obviously I subtract 1 here, and delta's got to be greater than or equal to negative 1. That's pretty simple. And then here I subtract 3 over, lost my mouse, and delta's got to be greater than or equal to negative 3. Alright? So we end up with these two restrictions on delta. Now, I have to take the one that is most restrictive, okay? I have to take the one that will give me the smallest delta, because if I were to put these on a number line and think about it, here's the idea. So here's 0, here's -1, here's -3. And I'm allowed to let delta, I need delta to be less than or equal to 1 and less than or equal to -3. And if it goes past one of these two constraints, then this choice is no longer optimal, okay? So if it goes past -1, it's no longer optimal, and I don't want to go there. If it goes past -3, it's no longer optimal. But notice if I pick a value right in there, like -2, I have broken this optimality. I've gone past -1. So I always take the more restrictive of the two. So delta has got to be greater than or equal to -2. So now I should be able to give you what my new cost can be. Okay? The original cost was what, 3? And what we need this to be is we're adding delta to it. Well, delta happens to be -1. Our delta needs to be greater than or equal to -1. Let's say that. So let's write it in this way. Well, delta has got to be greater than or equal to -1 or -1. So our cost has got to be greater than or equal to, so let me change that from an equal sign, 2. So I'm allowed to let this cost change, and as long as it's bigger than 2, this choice that we have made or that we have found to be optimal, this choice of x2 and slack 2 will stay the optimal. So that's how you perform sensitivity analysis on a cost, especially a cost that is a basic cost or a basic variable. Let's do a right-hand side. Let's look at B1, or the first right-hand side. So I'm gonna, let's just grab all this and copy and paste it over into our next slide. Let's go back and let's get our B inverse. Paste. Alright, now when we're doing sensitivity analysis like we're fixing to do on the right hand side, what we're wanting to do is to check that it's going to stay feasible. Well, this right hand side here in the final table is just B inverse lowercase b. Okay, so let's do sensitivity analysis on B1, which B1 is 10 right now. We're going to add delta to it to see how much change it can have. Alright, now this formula is actually really simple then. So B inverse times B, which is going to be 10 plus delta 12. So let's write that out. 1, 0, -1, 1 times our new B vector, which is 10 plus delta and 12. So I need to perform this matrix multiplication. And once again, it's not too nasty since it has just mainly 1s and 0s. So 10 plus delta, so row times column, so 10 plus delta plus 0, negative 10 plus delta, or negative times 10 plus delta, plus 12. So let's see what that gives us for our two entries. Well, this one's just 10 plus delta, and this entry will be negative 10 minus delta plus 12. So if I simplify that, I have 10 plus delta, and I will have 2 minus delta. Now, to stay feasible, this right-hand side has to be greater than or equal to 0. So I just need to check both of these inequalities are greater than or equal to 0, and I can take them piece by piece. So 10 plus delta has got to be greater than or equal to 0, and 2 minus delta has got to be greater than or equal to 0. And I can solve them each for delta. So subtract 10, so delta's got to be greater than or equal to -10. And over here, if I look at this, I can subtract 2 and then divide by -1, or add delta over. But either way, delta's got to be less than or equal to 2. Okay? So, the original value of b was 10. I'm allowed to go as small as subtracting 10 from it and as big as adding 2 to it to stay feasible. So that would be like 10 minus 10 and 10 plus 2. So our real value of b1 has got to be in between 0 and 12. If it's in between 0 and 12, we will stay feasible. Alright, and that's how you perform sensitivity analysis on a right-hand side. It's a really easy just b inverse times b. And the one we're performing sensitivity analysis on is going to be the original number plus delta. And you just do the matrix multiplication and say each of these pieces needs to stay feasible, so greater than or equal to 0. So after you do your matrix multiplication, see what delta can be, see what the change can be. The change can be down 10 or up 2. And that's all the values it can take. Alright? I hope this helped clear up a little bit of sensitivity analysis.